the problem that you guys just submitted in your quiz. So we're looking at the first part where we need to set up all the governing equations for this particular system. And they're saying that you will end up with two differential equations, and I did get a lot of questions on students saying that they have more. How are we supposed to reduce that? So what happens is that, and as you will see later on, is that you have an extra redundant expression that you can kind of plug into the other two to get just two equations that have just two unknowns, which is the position of the piston, x, and the angular velocity of the pump, omega. So just those are the two kind of variables that we can tune our system for. So let's start off with the torque balance expression first. And so what I'm doing right now is I'm just focusing on this small fraction over here. And that's kind of looking into the input power of the system. This is where I'm looking at my torque balance like we had done last week. So that would be the inertial moment, Gp, times the angular acceleration, which is equal to Tp. Now there was some confusion. So here Tp is your input torque. Generally what we are taking Tp as was the torque over here, which is going directly to the pump. But here it's the original input torque. And we'll just call the pump torque T in this case, and that would be equal to dP times delta P. So you have minus Bp times omega P. So that's modeling the frictional losses, minus dP delta P. So that's the pump torque that I was talking about. And as you can see here, the delta P is again between, so what's coming out of the pump is at pressure P1, and what's going into the pump is at pressure P equals 0. So the difference between them, delta P here would be P1 minus 0. So delta P for our case here turns out to be just P1. So any questions so far? All right, now let's move on to our flow equation. So here I'm calling QP, which is the amount of flow that's coming out of the pump, which is equal to Q leak. So some of the flow is going and leaking back into the pump, and plus QV. And QV is nothing but the flow that's going out over here, and finally causing the piston to rise. So that's what I'm calling QV. Right. So now let's simplify these in terms of in terms of the characteristics of the pump. So we have dP times omega P, and Q leak, as you guys remember from last time, that was the pressure drop divided by the resistance of that particular the leakage resistance for that pump. So that would be again P1 divided by R leak plus QV. So QV we can write down as, let's say it's going through this valve. The flow going through this valve would be basically equal to the pressure drop P1 minus P2 divided by the resistance that this valve is offering. And that's kind of analogous to how voltage, current, and resistance also works, right? V by R is equal to current. Current is analogous to the flow that we are looking at over here. So we have R. And before we move forward, let me start numbering these equations because we're going to have a lot of them for this particular part. So this is equation 2. The one before that I'm calling that equation 1. Any questions so far? All right. So finally then we have the equation for our piston. So now we are looking at this object over here. So there will be some hydrostatic force that you're learning about in ME 3503. So there's some force coming in from the fluid below, hitting the piston head, and then there will be some force coming in from the spring from the top, and that would be equal to the mass times acceleration of this piston head. So we have mx double dot is equal to the hydrostatic force coming from the bottom minus kx, the spring force. And I'm going to call this expression 3. Now, in the last section, I remember some student asking me that we are not considering the weight of the piston head itself. And that's true, we have ignored that in this particular case. But if you do have that extra term involved, let's say in your quiz solution, I mean, I'd tell the grader not to deduct points because that's not incorrect. You are considering an extra force that we have neglected over here. So if you have had that expression extra, that's fine. Any questions on that? All right. So moving on to expanding what this hydrostatic force is. So this is equal to P, that's pressure, and that will be a function of x. And keep in mind here that x is denoting elevation, not the horizontal axis, but rather the vertical one. Px times the cross-sectional area of the piston head. And the pressure here can be written as P2 minus rho g times h naught plus x. So that's nothing but the weight of the fluid. So this is the pressure, P2 is the pressure at this height elevation here, and then as you go up, the pressure will reduce due to the weight of the fluid itself. So any questions on that? I'm going to call this equation 4. All good? All right. So now let's look at another kind of expression that will come in handy to drop these the first three equations into just two equations. So QV, as I discussed earlier, is P1 minus P2 divided by R. So that's one way of writing it. But at the same time, that same amount of flow, and since mass is conserved, that same amount of flow is also what's causing this piston head to rise up, right? So whatever volumetric change happens as the piston moves, that's equal to the volumetric flow rate that's coming in from here. So this can be written down also as A times x dot. So we have the original expression that we used before, and then that's equal to A times x dot as well. Does that make sense? Any questions? All right, so what I'm going to do now is rearrange this expression a little bit to get P2 is equal to P1 minus RA x dot. Let's call this equation 5. Now let's plug in 5 back into 2. So we'll have let me call this 6. So you can see that we now have an expression for pressure in terms of the location x and the angular velocity omega. And using expression 6 and 5, we'll get an expression for P2 as well in terms of just the location x and omega. And then you can plug P2 and P1 back into 1 and 3, and that's how you have reduced the 3 equations to just 2 equations. So let's plug in 6 into 5. So from equation 6 and 5, you will have let's call this equation 7. So any questions so far? Does it all make sense? All right. So now what we can do is we can plug in equations 6 and 7 into 1 and 3, and that way we will get our final two equations that we are looking for. So let's go ahead and do that. So from equation 6 and 1, what I'll finally get is an equation that looks something like this. Now I have grouped the angular acceleration, the angular velocity, and the x terms together so that we can write it as in a matrix form very easily later on for part 2. So we have dp square r leak times omega p minus which is equal to dp. And then similarly, what we can do is we can also write down or model the piston motion equation. And that would be from 3, 4, and 7. So after you use all of those equations, you will end up with an equation that looks something like this. Let me call these equations 8 and 9. So these final two equations 8 and 9 are what they're asking us. So this is what we're looking for. So as you can see, we have two equations, and the only two variables that we are accounting for here is the location x and then its derivatives, so the acceleration and velocity of the piston head, and then omega p, which is the angular velocity of the pump, and then also its derivative, which would give its angular acceleration of the pump. So does that make sense? Any questions? All right. So for part 2, what we need to do is we want to calculate the system transfer function. And so for doing that, we're going to first write, we're going to do the Laplace transform for both of these equations. And then we'll write it in the matrix form, and then use Cramer's rule to come up with the transfer function. So Laplace transform of 8 and 9 would basically give you two expressions that look something like this. So that's the first equation, and then the second equation is xs, and that is equal to 0. So what I've done here is, you remember there was an h naught term over here on the right hand side. But since we are saying that we can assume 0 initial conditions, what we are saying is that the elevation initially h naught was just set to 0. So we have assumed h naught over here to be 0. So those are the two equations that you get once you have performed the Laplace transform. So any questions on that? In case you miss out on writing anything, that's fine. I mean, everything will be posted on Carmen, so don't worry. All right, so what the next step is a little time consuming to write down. So what I've done is I've written it beforehand. So I've written the two equations in its matrix form over there, and as you can see, it's a 2 by 2 A matrix, and then this is the x that we are solving for, and this is the b on the right hand side. And then using Cramer's rule, we can come up for an expression to solve for the location x, and if you evaluate the determinant of this particular numerator, you will end up with a TPS that's multiplying over here. You're just taking that to the bottom. That gives us the transfer function, and there you go. So that's what we wanted to evaluate. We wanted to evaluate the transfer function of xs is to the torque. So does anyone have any questions on this? All looks good. All right.